It's a good time to pause and think about the big picture of first year calculus before we jump into the second semester. That whole first semester, the big idea there was, how do we find the slope of a curve? So how do we find the slope of a line tangent to the curve? We learned lots of methods for finding that slope. We learned to call a function that gives that slope anywhere the derivative. So finding a derivative we call differentiating. And so we sometimes call that whole first semester calculus differential calculus. It's all about finding derivatives and then using derivatives to solve problems. Because it's going to help us make a connection to second semester. Just recall that sometimes we needed a slope of a tangent line. We needed a rate of change. We wanted to approximate instantaneous rate of change, but we didn't have enough information to actually do that with calculus and algebra. So we could sometimes approximate a derivative by using the average rate of change formula, and that's the same as finding the slope of the secant line. So change in y over change in x. Or average rate of change. So we're going to do second semester. We're going to focus first on finding areas under curves. This is what actually happened when calculus was discovered. We had one group of people who were working on figuring out the slope of a tangent line. Another group of people, some of those people overlapped, were interested in finding areas under curves. And all of a sudden they figured out one day that the two problems are actually related, even though they seem like they're unrelated. So we're going to learn to use this term integral to talk about an expression for an area under a curve. So this second half of calculus is sometimes called integral calculus. We're going to study integrals the second semester. One of the big topics for us, once we talk about how to find areas under curves, is to notice how the two problems, slopes of tangent lines and areas under curves, are related. It's such a big deal, we call it the fundamental theorem of calculus. It talks about those two, the way the two problems are related. So we're going to start here in 6.1 with a little harken back to, how did we start to think about slope of a curve? Well, at first we didn't know how to do it, so we talked about approximating it with slope of a secant line. So that's how we're going to introduce our discussion of finding an area under a curve. We're going to focus on, well, how would I figure out the area under the curve using an approximation, using an estimation? And that's going to lead us pretty soon to an actual algebraic and calculus way to find area under any curve. So I'm going to read here. As with differential calculus, one of the most important skills for understanding integral calculus is to figure out how to estimate this area when no exact answer can be found. To estimate the area under a curve, we're going to use geometric shapes to break up the big area into smaller areas that we're going to add together. You learn that in geometry. If you have one big area and you're not sure how to find that area using formulas, you can chop it up into smaller pieces. So we're going to start today by chopping up into rectangles and later trapezoids. Like maybe after they're finished mowing the lawn next door. So here we are. First semester, how do you find the slope of a curve? Second semester, how do you find the area under a curve? And the super cool way that the two problems turned out to be connected. But before we understand how to find area under a curve, I want to understand a little bit why mathematicians cared so much at the time about how to find area under a curve. So to help us see, you can follow along in your textbook on page 269. Imagine this problem that you've been doing for a long time. You have a train going 75 miles an hour. How far does the train go between 7 a.m. and 9 a.m.? Well, you know this formula you probably learned a long time ago, rate times time equals distance. So you figure out the difference between 7 a.m. and 9 a.m. is 2 hours. And you multiply that time, 2 hours, by the rate at which the train was traveling. Since the rate is measured in miles per hour, and your 2 hours is measured in hours, you know when you multiply rate times time, that miles per hour times the hours are going to cancel and give you an answer of 75 times 2 miles. So you can see that picture in the book. If we think about the curve, y equals 75, it's a constant, right? The train is going at a constant speed. So when we find the area under y equals the speed between 7 and 9, we're actually finding the area of a rectangle 2 hours wide by 75 miles per hour high. 75 miles per hour times 2 hours to make 150 miles. So what if the velocity is not constant? Would finding the area under the velocity curve still give distance traveled? Well, mathematicians worked a long time on it, and it turns out that yes, we can decidedly say that the area under velocity curve gives distance traveled. So that is important. Area under curves fact number 1. If velocity is non-negative, we'll talk later about what to do if it's negative, but if the velocity is non-negative, then the area under the curve, under the velocity curve, gives distance traveled, as long as you have chosen your measurements correctly and in a way that the units match up. So, now that we know this, we are armed with important area under curves fact number 1. The area under the velocity curve between the time units that you care about give the distance traveled during that time interval. So watch what I can do. I can actually find distance traveled for non-constant velocities. That's what makes this important, is how many trains do you really know that travel at a constant speed the whole time that they're traveling. So I can find the area under a velocity curve to find that distance. So here's an example. I have a velocity, and I know the velocity happens to be 3/5 t plus 4. And here's my velocity curve. This is time. This is going to be a velocity. And I'm interested in the distance traveled over the 5-minute time interval, 0 to 5 minutes. So, and velocity is measured in miles per minute, and I'm going to measure time in minutes. This is miles per minute. So this 3/5 t plus 4, that's a linear function. So I'm going to 1, 2, 3, 4. 1, 2, 3, 4. I'm going to have a v-intercept, I guess, of 4. And I can graph this using the slope and the y-intercept. So I can imagine now rise over run, 1, 2, 3, and over 1, 2, 3, 4, 5. I'm going to make my graph of the velocity curve. So that is not a constant. I can tell it's not constant. It has a slope of 3/5. And if I think about the area, that's time 0. This is time 1, 2, 3, 4, 5. If I could think about shading in that area, I can recognize that as a trapezoid. So we'll have a little reminder about how to compute the area of a trapezoid. A trapezoid has 2 parallel sides. So we find the area of the trapezoid by averaging the 2 parallel sides. So for me, my parallel sides happen to be vertical. They're this one and this one. Well, this has a height of 4. This has a height of 7. So I average the 2 parallel sides. So 4 plus 7 over 2, divided by 2 is what averages them. I'm going to multiply by the distance across the other direction. Well, that's this distance here, which happens to be the distance across my time interval. So from 0 to 5, the distance across that time interval is 5. So you can think of that 5 as being measured in minutes, and this 4 and 7, they were each y values here, each being measured in miles per minute. So the average of two quantities measured in miles per minute is also measured in miles per minute. So I'm going to have 4 plus 7 over 2 miles per minute times 5 minutes to make 11 halves times 5, 55 halves. Miles per minute times minutes. The minutes cancel out to leave units of miles. So I just did it. I figured out the distance traveled by something traveling at a non-constant speed. And that's my big idea here. If I can find the area under the velocity curve, that's distance traveled. So we're going to do a similar example. Again, I'm going to have a velocity curve. It's going to trace out a shape that I recognize from geometry, and I'm going to say that the distance traveled is the area under the velocity curve. And I'm going to use my geometry powers to figure out that area. So we have to start to recognize this expression. I have a velocity v of t equals the square root of 16 minus t squared. So just remember briefly, x squared plus y squared equals 4, for example. 16 is a better example. So this should be x squared plus y squared equals 16. Trouble getting my 2 in there. So I hope you'll recognize this from geometry or algebra 2, wherever you, or pre-calculus, wherever you got it, as an equation for a circle whose center is 0, 0, and whose radius is the square root of 16, so in this case the square root of 4. I want you to think about what would happen if you tried to isolate the y in this expression. So what if you were trying to write this equation but make y a function of x? You would try to isolate the y. You might write y squared is 16 minus x squared to isolate the y term, and then you would take the square root of both sides in order to undo what was happening to y. But you know, when you take the square root, you're going to have to add a plus or minus sign. So you'd end up with y is the positive or negative square root of 16 minus x squared. So if you left off the plus or minus sign, like you can see here, this has no plus or minus sign. But I hope you'll recognize that as just the equation of a circle whose center is 0, 0, and whose radius is 4, the square root of 16, but just the top half, where the x-coordinates, well, where the y-coordinates are positive. Because if you don't have this plus or minus sign, you're not going to have any of the negative x-coordinates. Just notice here, if you end up with like a perfect square minus your variable squared inside a radical sign, this is probably the equation of a circle that you tried to isolate the y in, and so in this case ended up with a semicircle. So my velocity curve here is going to be a semicircle whose radius is 4. I'm going to sketch that in here. That's not really big. Okay, that is a semicircle. We're going to just go with that. I appreciate your patience. So here I have a semicircle, radius 4, and now this is my velocity curve. If I want to find the distance traveled between times 0 and 4, I'm going to find the area under the velocity curve between times 0 and 4. If I shade that in, here I'm going to use red, that's a quarter circle. So I'm going to find the area of this quarter circle. That's going to be 1/4 times the area of a circle, pi r squared. So pi r squared, in this case the radius I know is 4. So the distance traveled is going to be, I have centimeters per second times seconds. So I'm going to have 1/4 pi times 16, so it's going to be 4 pi. 4 pi centimeters. final answer.